Hello and welcome. In the previous lessons, we have learned about the stack and stack pointer. We discussed that the program stack is used to store local variables, parameters passed to a function, and return address. In this lesson, we shall practically examine the program stack. Here is a simple C program to examine the stack. There are two functions, main and f1. f1 is called from function main. Both the functions define a couple of local variables and logic to print the address and data of the program stack. The global variables fun underscore level, sp underscore level, and stack underscore level store the levels used in the program display, and sp underscore ASCII and data underscore ASCII are used to pass data between functions. The program uses teraterm or screen over serial communication to display information to the user. The functions defined in the usart.c are used to initialize the usart and display character and string. The function init underscore usart initializes the serial communication and takes the baud rate as a parameter. We are using the baud rate of 9600. The function sprints displays a string. The string must be null terminated, meaning the end of the string is marked with a null character. The function sprintc is used to display single character. The functions sprintcr and sprintnl print carriage return and new line characters respectively. The functions underscore int to ASCII hex and underscore char to ASCII hex defined in util.c convert the stack pointer address and data to ASCII string. Both the functions take two parameters. The first parameter is the address or data, and the second parameter stores the address or data converted into ASCII string. The function main starts with initializing the usart and prints the function label followed by the function name on the UI. Then the assembly instructions read the 2-byte stack pointer. The IO registers 3E and 3D are the high and low byte of the stack pointer respectively, which are read into the variable sp underscore val. We shall learn about using the assembly instruction in C code in the later section. The address pointed by the stack pointer is printed next with the label. Finally, the for loop prints the stack frame. It prints the data and the corresponding address of the stack in different lines. Then, the function f1 is called from the function main. The function f1 also implements the same logic to print the function name, stack pointer, and stack data as shown. The function accepts the stack pointer from main and prints the content of its stack frame only. We need development board with the base circuitry connected to the development PC through USB serial adapter. The details of the base circuitry and wiring of the USB serial adapter is discussed in detail in the previous lessons. Remove the optimization flag -os in the make file and add the -g flag. The -g flag instructs the compiler to retain the debug information in the object and the executable ELF files generated during the compilation. Compile the program with this change and flash the development board. Launch the teraterm or screen and you will see the stack frame for both the functions displayed. Let's quickly understand the format of .asm file. The file shows the C statements followed by the corresponding opcode and assembly instruction emitted by the compiler. The first column in the assembly code line is the address. Then the 2-byte opcode of the instruction follows after a colon. Then the human readable instruction in assembly language is displayed. For now, we shall focus on the aspects related to the program stack. The interrupt vector table, ISR, do copy, and BSS copy will be dealt in the later section. However, these code come from the interrupt.c file. Now, let's walk through the disassembly file and understand the stack frame. The stack pointer must be initialized to the highest memory address of the SRAM, that is the address 08FF in case of Atmega 328 microcontroller. It is done in the ISR of reset interrupt defined in the function __reset_ISR in the file interrupt.c. The registers R28 and R29 are loaded with FF and 08 respectively, and the content of the registers is stored in the stack pointer, which is the IO register 3D and 3E. The first two instructions in the function main pushes the registers R28 and R29 on the stack, so the first two bytes in the stack are FF and 08. Then the function main calls the instruction rcall twice. The rcall instruction jumps to the address relative to the offset and decrements the stack pointer by 2. However, the offset in both the rcall instructions is 0. Hence the stack pointer is decremented by 4 and program counter is unchanged. Now the stack pointer points to the address 08F9 and the same is displayed in line number 2. The compiler calculates the size of the stack required for a function during compilation. In function main, we are using two local variables, hence the compiler allocated space for two integer type variables by using rcall twice. Let's not bother about the content of the address 08FD to 08FA. We shall investigate how these addresses are being used and manipulated in a while. Note the in instructions after the rcall. These instructions store the SPH and SPL to the registers R29 and R28 respectively. The register pair R29 and R28 is collectively referred as register Y. The assembly instructions shown are used to copy the stack pointer in the local variable sp_val defined in the function main. Let's look into the assembly code generated for these two lines. In the first set of instructions, the IO register 3E, which is the SPH, is copied to R25 and the pair R25 and R24 is stored in the address pointed by Y+4 and Y+3. Similarly, in the next set, the IO register 3D, which is the SPL, is copied to R24 and again the pair R25 and R24 is stored in the address pointed by Y+4 and Y+3. These instructions effectively copy the stack pointer which holds the value 08F9 to addresses pointed by Y+4 and Y+3, and Y+4 and Y+3 point to the addresses 08FD and 08FC respectively, since the register Y contains the address 08F9. Hence the addresses 08FD and 08FC now contain a copy of stack pointer which is the value 08F9, and the addresses 08FD and 08FC are allocated to the variable sp_val by the compiler. Now let's understand the uses of addresses 08FB and 08FA and why these are holding the values 08 and FA. Examine the assembly code following the for loop. These instructions correspond to the initialization statement of variable pointer. In these instructions, the register R25 and R24 are loaded with the values 08 and FF and then stored in address location pointed by Y+2 and Y+1. Since the register is holding the address 08F9, y plus 1 points to the address 08FA and y plus 2 points to the address 08FB. Effectively, the addresses 08FB and 08FA are allocated for variable pointer and are loaded with the values FF and 08. However, the values at the addresses displays different value. This is due to the for loop in which the variable pointer is being decremented and used to display the address in the stack and their data content. The for loop executes until the address pointed by the variable pointer is greater than or equal to the value held by the stack pointer. Hence, the address corresponding to the variable pointer is displayed the value 08FA after being decremented by 6 before getting printed. Let's quickly examine the stack frame for the function f1. The content of the stack can be explained in the similar manner as that of main, but there are few differences. The first 2 bytes of the stack frame holds the return address. The program execution jumps to this address after the function f1 returns. The instruction call in the function main pushes the program counter to the stack before jumping to the function f1. The function f1 starts with pushing the registers R29 and R28 on the stack. The register pair was initialized with the value 08F9 in the function main. Hence, the stack addresses 08F7 and 08F6 contain the values F9 and 08 respectively. We are using 3 local variables in the function f1, including a formal parameter. So, the compiler has allocated the memory space for 2 integer type variables and 1 character pointer using 3 rcall instructions. The stack pointer is decremented by 6 due to rcall instructions and points to the address 08EF. The address pointed by the stack pointer is stored in the register pair R29 and R28. That means the register Y points to the address 08EF. Notice the 2 std instructions which stores the register pair R25 and R24 to addresses Y plus 6 and Y plus 5. The register pair is used to pass parameter from the function main to the function f1, and the pair was assigned with the value 08F9 before calling the function f1. So, the addresses Y plus 6 and Y plus 5, that is 08F5 and 08F4, is assigned with the values 08 and F9. The addresses 08F2 and 08F3 are allocated for the variable sp_val in the function f1. It stores the stack pointer and hence the values fe and 08. And the addresses 08F0 and 08F1 are allocated to the variable pointer. These variables are assigned and manipulated as that in the function main, hence the values as displayed. The data pushed on the stack and addresses allocated on the stack is released by calling pop or similar instruction before returning from the function. It is difficult to identify the stack addresses allocated for local variable. However, examine the assembly code and the value in the stack, it can be accurately guessed. From the example of 2 stack frames, we saw how compiler allocates physical memory space for local variable and formal argument, and return address is stored on the stack. The set of addresses along with the data content is called the stack frame of a function. With this, we come to the end of this lesson. I hope the examples of stack frame clarified the concept of program stack. The lesson also includes a handout for further exercise on stack. Thank you and happy coding.